What's going on, everyone? Johnny Bannon here, and today we're going to be going over domain 1.7 in our Network Plus N10-009 full course. This domain is all about IP addressing. So we look at the exam objectives, and we'll bring those up right now. I have them on my slide deck here. They don't really tell us to do a deep overview of IP addressing. They tell us to explain some concepts, public versus private. They tell us to explain subnetting and some of the acronyms there. Then they tell us to go over the different classes. Well, what I'm going to do in this video is I'm going to take you through how to actually break down an IPv4 address, the basics IP addressing, the basics of binary, how to subnet. Now, again, we're not going to dive deep. I have a subnetting video, a CCNA course I'm going to attach to this playlist and in our self-paced course. But this video is going to be just going over the basics, getting you to understand what an IP address is, what a network is, how the subnet mask is laid out, the binary behind it, and then we'll go hit the actual exam objectives that CompTIA wants us to know about. So to get started, I'm going to go to my whiteboard here, and let's just start talking about IPv4. So some basics. So IPv4 is a 32-bit address. So IPv4 is a 32-bit address that we see as dotted decimal. So the human readable format as an IP address, which you may be used to, probably looks something like this. And this is what we call dotted decimal. Now each number here is going to be 0 through 255. That's the range. And it's called an octet. And it's always separated by a dot or a period. Now, when you read off an IP address, you say 192.168. I've never personally heard 192 period, 168 period, but each octet separated by a period or a dot here. So I'll put period or dot. Now, each octet is equal to 8 binary bits. 8 binary bits. And we're going to break down how we convert dotted decimal into binary. So again, this is what we see as humans. We are able to read and understand this number, 192.168.1.0. Computers, though, they do not talk in English or Spanish or any of our languages. They talk in ones and zeros. So this IPv4 address is made up of total 32 bits, 4 octets, 8 bits each of ones and zeros, binary. Now we're going to break that down in just a second. Another key component is something called the subnet mask. The subnet mask, let me just rewrite that K there, subnet mask, is going to be how we tell the difference between what's called the network portion. Then red is going to be the network portion. And the host portion. The host portion. And we're going to break this down further. But what you need to know is that subnet mask is there to define, hey, these are the octets, the binary that belongs to the network. And then this host portion is what's going to be unique to each device. Now, an IP address works in layer 3, the network layer of the OSI model. An IPv4 address, is assigned to nodes or to hosts. So each computing device that wants to talk on the internet or your network or your local area network needs an IP address. And each device is going to have its own unique IP address to be able to talk within its network or to talk on the internet. Now, of course, we're going to talk about public versus private when we get to the slide deck. But just as a good fundamentals, foundations, every single computing device that wants to talk on the network or the internet needs its own unique IP address. Okay, So now that we got some of those basics out of the way, let's go in and do one thing first. We're going to do a couple things. But the first thing we're going to do is convert dotted decimal, the human readable format of IPv4 address, into binary. And then binary into dotted decimal. And then from there, we're going to look at our subnet mask and break down how our subnet mask or our CIDR or our prefix length, yes, that's we're going to go over a lot, defines the network side and the host portion, and how we can use a subnet mask to determine how many IP addresses we're going to be able to assign, how many unique IPs we have, and how computers determine what network they're in, so they can talk to other nodes or computers or internet connected devices in their own network. So first, let's go ahead and break down, actually we're going to come over here, how we convert, let's see, dotted decimal into binary. Now what I have here is my binary conversion chart. Okay, so I'm going to label this. I'm going to put this over here to the right, and let's talk about this. So this is going to be what's called my binary conversion chart. So we have our bits. So ones, our 1 bits equals on. The zeros equal off. So when we look at a real number, a human readable number, like let's convert 192 into binary. We're going to use this binary conversion chart. And this is going to be binary conversion, the basics of binary as far as it relates to IPv4 and IP address. So if you can see here, we have 1, 2, 3, 4, 5, 6, 7, 8 numbers here. And this is going to go in the powers of 2. So you can see, if you go to the 2 to the power of 8, right? And we add all these up, that's going to equal 256. However, in computing, and this is going to be something you're going to have to get used to, it actually equals 255 because 0 counts as a number. So if we go in and add all this up, so 1 plus 2 is 3, plus 4 is 7, plus 8 is 15, 15 plus 16 is 31, plus 32 is 63, plus 64 is 127, plus 128, that's going to equal 255. But what you don't see is that 0 counts as 1. So if I were to do 2 to the power of 8, that would equal 256. So we go in powers of 2 when it comes to binary, right? And like IP addressing, but 0 counts as 1. So it actually 255, okay? Now without confusing you too much, I'm going to erase this and move on. Because we're here for one reason. And that is to get you to convert dotted decimal format, or our human readable format, into binary. So here's how we do it. So we take our binary conversion chart, and we're going to take this real number, we're going to put it above here. And we're going to say, is 192 greater or equal to 128? Well, it's greater. If it's greater or equal to our binary conversion chart number, the number we're converting to binary, it's a 1-bit. And then we're going to subtract that number, that original number. So 192 minus 128 is 64. And we're going to say, is 64 greater than or equal to 64? Well, it's equal. That's an on bit. And then we subtract, and what do we get? Zeros. So if we want to convert the number 192 into binary, this is what those 8 bits will equal. Now let's do this for the number 192 dot, let's say, 174. So I'm going to clear this up a little bit. 174. Is that greater or equal to 128? Well, it's greater. That's a 1-bit. So 174 minus 128. I'm not good at public math because I'm recording, so I feel like I'm talking to you Like, this is public speaking for me. 174 minus 128 is 46. Is 46 greater than or equal to 64? It's actually less than. Off bit. Is 46 greater than or equal to 32? It's greater. On bit. Subtract, and what do we get? That is 14. I can do that public math. 14. Is it greater than or equal to 16? It's not. It's less than. Off bit. Or 0 bit. Kind of got a little bad writing there. It's okay. It's a 14 though. 14 is greater than or equal to 8. So that's 1. We're going to do some subtraction. 14 minus 8 is 6. Right? This is embarrassing. 14 minus 8 is 6. 6 is greater than or equal to 4. On bit. 6 minus 4 is 2. On bit. And then, of course, 0. So to convert 174, that's our dotted decimal format, 0 through 255, we get 1 0 1 0 1 1 1 0. And that's how we do our conversion, guys. From binary to, from dotted decimal to binary. Now, let's erase this again. And let's do a different conversion. Let's try to actually convert from binary into dotted decimal. All right, so let's do it. So I'm just going to write random binary. So let's say 1 1 1 0 1 1 1 0. It's actually probably going to be easy. But here's how we convert binary into dotted decimal. So what we're going to do here is we're going to line them up. So I'm going to line this up underneath our binary conversion chart. And I'm just going to add the ones because that's a value. So 128 plus 64 plus 32 is 224. Then 8 plus 4 is 12. Plus 2 is 14. 224 plus 14. Over here off to the right, you can't see it, but it's my phone's calculator. 224 plus 14 is 238. So that equals 238. All right, awesome. Some of you may be looking at this, but like, well, this is easy. If I know all these numbers equal 255, that's a bad 25. Hold on, I'm trying to get better at writing in my videos. I could have just minus 255 from 16 and 1, and that would have got me my answer. And you're right, but, I'm just showing you the foundational way, the fundamental way to do it. So, okay, awesome. So I'm not going to spend any more time on here. That's how we convert from dotted decimal into binary, and that's how we convert binary into dotted decimal. Okay, so now let's move on. So now that we understand an IPv4 address is 32 bits, or 4 bytes also, because a byte equals 8 bits. So I'm going to write that up there too, over here in this space. It's also a 4-byte address, 32-bit or 4-byte address. Just some extra knowledge, right? 1 byte equals 8 bits, okay? So it's also a 4-byte address as well. Just want to write that out. So let's review. An IP address is 32 bits or 4 bytes. It's represented to us as humans as dotted decimal. We convert it to binary, though, as computers. The numbers are ranged 0 to 255. Each 0 to 255 is separated by a dot or a period. We call those octets. And then with our IP address, we're always going to have a subnet mask that determines the network portion and the host portion. Now let's get into subnetting. So to do this, here's how we're going to start. Okay, I'm going to bring that binary conversion chart back over here in just a second. So let's go over, what a network is. So let's say this is our network. I'm going to make my font a little bit bigger. 192.168.1.0. This is our network and our network address. We'll learn what that is. So this is our network address. So here's our local area network for an example, okay? It's a local area network. We're going to have these nodes, these computers. .2, .3, .50, .70. Okay? All these computers are in the same network. But how do we determine that? Well, we said this is our network address. And just to let you know, the network address or the network ID is always the start of a network. Always the start of a network. Well, we always have a CIDR or a subnet mask or a prefix length, all synonymous, okay? So let's say this is, and let me adjust this just a little bit here. This prefix length or subnet mask is /24. So what does that mean? So a /24 means that there is actually 24 network bits. 24 network bits that represent the network portion, and 8 zeros or host bits that represent the host portion. So let's write out our subnet mask in binary and in dotted decimal, and let's go over what the network portion is and the host portion. So I'm going to write a couple things out here. So our subnet mask. Subnet mask. So it's a /24. In dotted decimal, that is 255, 255, 255.0. In binary, and I'm going to change my thickness, each one of those octets looks like this. So we have 24 ones. You see, /24 is 24 ones. And I swore I was going to get better at handwriting, and I'm going to keep that promise. Okay? And then the rest are zeros. Okay. Kind of ran out of space there a little bit. Cool. So we got that. So if this was a /25 instead, so let's say we wrote out a /25 instead, the binary would be 25 ones. .25, and then the rest would be zeros. And the dotted decimal would look the same for the first 3 octets of this subnet mask, and then it'd be 128. We're going to get there, okay? You're going to ask me how am I getting that 128. We're going to get there. So I want that just to be known, that slash, that CIDR notation, /24, /25, means that there's 25 1 bits. And subnetting, when we look at a subnet mask, the ones, this is for subnetting, are the network bits. Okay? And the zeros are the host bits. So that's in subnetting. The ones are the network bits and the zeros are host bits. So let's compare the IP address, our network address now, the subnet mask. So remember, we said, okay, here's our network, here's all of our computers. But how do they know they're all part of the same network? Well, we take that network ID, okay, and we say 192.168.1.0 is this subnet mask, 255.255.255.0, and we convert both of these to binary. So this in binary would be 1, 1, all zeros, the rest zeros, excuse me. 168, I think it's something like, I'm going to pause the video to do this. And then all zeros for the rest of it. Okay. So that's our network ID. Now what I'm going to do here is convert the subnet mask, and I'm going to give it a different color. I'm going to give it like green, okay? And let's write this out in binary and line it up. Didn't line that up as good as I wanted to. That's okay. And then the last octet will be red. Okay. So what do we have here? And I'm going to move these one's just a little bit over. Okay. So what we're saying here is that these ones represent the network portion. Okay? They represent the network portion. These zeros over here represent the host portion. So now when I assign this computer .2 with a /25 subnet mask, okay, and I'm gonna zoom this over here, with a /24 subnet mask, I know that I fall within here, this side. So okay, so then the rest is the network portion. So I know as this computer that if I'm 192.168.1.2/24, because I also get a subnet mask as a user, I know, I have to get a subnet mask. I know that on the left side here is my network, and on the right side is going to be all my buddies in the same network with another unique IP address. So if I want to talk on my local network, I could talk to anybody in this range, .0 through .255. Now you may say, well, how does it know that? Well, you see these host bits? If I were to line those host bits up against my binary conversion chart, so my binary conversion chart is 128, 64, 32, 16, 8, 4, 2, 1. If I line all those bad boys up and add them all together, right? That equals what? That's going to equal 255. So that means as a computer, I know, okay, the network, the subnet mask is telling me that all these zeros are for the host. Well, I fall within that. I know my network. Now my host range is going to be 0 through 255 because I'm .2, so I fall within that range. So everybody else within that range is in my network, and I'm a part of their network. And that is as fundamental as bare bones I can talk about subnetting. Okay, now, if I were to make this a /27, how would that work? So let's come down here. So let's say I have a /27. So 192.168.1.0/27. And let's say I have some computers. So I have PCA here. And this is going to be 192.168.1.10. I have PCB here. And this is going to be 192.168.1.20. And I got PCC here. Some reason that PC is bigger. And this is .40. Okay. So they're each going to get a /27. Well, let's break this down. So /27, let's convert that to binary. So we'll start with our network ID. Okay, the start of our network ranges. And then it's a /27. So that means there's 27 network bits. So if I were to write that out, 8, 16 network bits in the subnet mask, 24, 25, 26, 27. That means the rest are the host bits. And if I write my binary conversion chart out over here, and I say, okay, what's the last octet of my subnet mask? I'm just going to line these up. 1, 1, 1. I add those together. That equals 224. Now, what's my host range? Well, I can take all these hosts, line them up, add all that together, and that equals 31, but 0 counts as 1, so really 32. And I can say my host range is .0 to .31. So now, looking at these computers and knowing what their last octet is, PCA and PCB are in the same network, but guess what? PCC is in a totally different network. Why? Because these two PCs fall within this range, and they know that because they're subnet masks. They know, hey, if I'm PCA and I'm 192.168.1.10/27, so here's my binary. That's not right. There we go. 101010000. Let's actually scoot this over a little bit. That's a great thing about this whiteboard. We can always give ourselves more space. Let's move this over. Okay. And then 00000001. And then 10, that's the 8 and 2. So that's 000, 128, 64, 32, 16, 1, 0, 4, 2, 1. All right, cool. And if we line up our subnet mask in binary, so /27 means what? 27 network bits in our subnet mask. 1, 2, 3. And then the rest are host bits. And let's make that line. Why not? That's how the computer knows its network. So it says, I need to be talking within this range here, okay? So, I know that I am in this range, 0 through .31, okay? Because I'm .10. And if I know that my network mask is only allowing me 31 other hosts to talk to, and I'm .10, and if I start at 0, that means .31, .32, .63. Here's all the ranges that could be possibly after .95/27. I know I fall within here, okay? And if we take PCC, I'm going to give myself a little bit more room, and we do the exact same thing. So I'm going to copy this and then make some adjustments. So if I'm PCC, I'm going to copy all this, paste, and let's make some adjustments. So let's do some erasing, right? I'm going to make sure that this is all in view. Okay. So this is .40. 40, and let's just change this, right? Oh, this is going to be the same, but what am I going to be after? I'm going to be, and this is 40, so it's going to be 0, 0, 1. Okay. And then 16, 8, 4, 2, 1. Well, if you look at that, .40 is outside my range. Y'all see that? It has a 1 bit over there. So you know it's not part of your network. So it's pretty cool how computers look at it for subnetting. Now, I'm not going to get deeper in how to do proper subnetting based on like host requirements. I'm going to I'm probably going to put in this playlist my CCNA subnetting videos because I would just be repeating the exact same thing, but this is for Network Plus. And to be honest, we just have to go over the definitions of variable length subnet mask and CIDR, classes interdomain routing. So when you see this /27, a /24, a /25, this is your subnet mask, your prefix length, and your CIDR, okay? And when you see, this is going to make sense when we come into classes. Let's say you see an IP address of 10.10.10.0/28. Well, this is variable length subnet mask, where essentially it doesn't matter what IP address, if 0 through 240 or 0 through 255 at the start, it doesn't matter. This is gonna make more sense when we get into class full addressing. We can put any CIDR notation for any IP address or any subnet, okay? This stands for variable length subnet mask. All right. Whew. If that was a lot, don't worry. I know. I'm going to pause this video, get back to our PowerPoints, and now go over what we need to hit for the exam objectives. But again, please feel free to go back, rewatch to go over the IP address basics, subnetting, and let's try to make this video not longer than an hour. And let's go back to the slides. Okay, so now we're back. So IPv4 overview, wow, we just went over this for a while, but again, just hit it. It's how devices communicate over the internet using Internet Protocol version 4. There's version 6 that we'll talk about slightly in our next section. 32-bit address. We see it as dotted decimal. Each number is separated by a dot, and it's 0 through 255. Awesome. We just learned all about that. Now let's go over public versus private IP addressing. So back when IPv4 first became the standard, when TCP/IP became the standard, and we're using IPv4, because there used to be other protocols like Apple Talk, and anyways, not to go down history lane, there was 4.2 billion addresses available. So if you look at, let me get my pen up real quick. If you look at IP addressing, it comes in powers of 2, kind of like I talked about. Well, that means if it's powers of 2, it's a 32-bit address, then that means it was 2 to the power of 32 is the total amount of unique IP addresses we could get. And it's like 4.2 billion. The actual number we could probably pull up if we wanted to, but 4.2 billion. So that means in the 70s and 80s, when this became the standard, that seemed like, oh yeah, we'll be fine. But quickly, even in the 90s, we started running out of unique IP space. Because remember, like we said, every single IP address has to be unique. So we did a couple things to combat this. First, we came up with classful addressing, where we had class A, B, C, D, and F, that the first octet number determined what class it was, and then it had to be in that class range. So like a /8 was for class A, a /16 is for class B, and a /24 is class C. So IANA, ICANN started saying, hey, we're going to give you a /8, and that's all you have, or a /24, and that's all you have, subnet from there of this public IP range, okay? Class D and E we'll talk about. Class D is multicast, E is like experimental. We have a slide on it. Well, then that still wasn't working. We were still running out of IP space very quickly. So we came up with classless. So with the a class A, it was 0 through 126 for the first octet was what it had to be. For a class B, it had to be 128 to 191 for the first octet. For a class C, it had to be 192 through 223 for the first octet. And then if you had an IP address that started anywhere in this range, it had to be a /24, and the same rule applied for class B and class A. We said, well, that's not good enough. So then we came up with classless. With classless, we said it doesn't matter, and this is where variable length subnet mask came in as well. You can have this, and it can be a /28. Cool. That helped us out a little bit. But still in the 90s, in the late 90s, and definitely in the early 2000s, well, in the 90s, we said that's still not good enough. We're still going to run out of IPv4 space before even the new, before Y2K. So a new standard was put out, an RFC, request for comments, RFC 19-18, which took 3 ranges, a class A, a class B, and a class C range, and named them private IPs. So if public and private IPs, or the RFC 1918 standard, we came up with private IPs. And this was to conserve the IPv4 space. So what that meant is that any organization's local area network could have a private IP range, and those ranges could be the same throughout all the different organizations. Every single organization can have the same exact private IP range. But when they came to their WAN connection, and again, this all depends if we're not doing carrier grade NAT, go down that road. Your WAN connection for the business, though, would get a public IP. And then we use a technology called NAT and PAT, which we're going to talk about later on in this course, that would translate your private IPs into public IPs. Now, I made this a /24 here, and I don't want to get any comments saying, hey, that 10 range is supposed to be /8. We have variable length subnet mask even with private IPs, but it split. The RFC 1918 standard said the private IP range are going to be as follows. We're going to have a class A range, okay, class A range, that would be 10.0.0.0 to 10.255.255.255/8, okay? So this /24 here, don't get don't get crazy on me, right? We can still have a big enterprise with internet protocol address management systems that we have 2,000 outsites, 2,000 spoke offices, and we can variable length subnet mask this /8 that we give our entire enterprise in the private IP range. Moving on. Then we had another private IP range that was 172.16.00 through 172.31.255.255/12. And then we had a Class C range that was 192.168.00, which you're probably used to. 192.168.255.255/16. And these are the private IP ranges. So an organization, every organization in the world could have the same 192.168.00/16 private IP range. These are not routable on the internet. These are not global, unique public IPs. They're just for your LANs, your local area networks, your campus networks to use in your intranets. Now you may say, how is this possible? If every single device needs to be unique to communicate on the internet, how do we not have routing loops everywhere around the world? Well, that's because on the WAN, on the demarcation point, on the upstream, the northbound, whatever you want to call it, facing the ISP, you're supposed to have an assigned public IP. So your routers at home do this, where if you go to Google and you type in what is my public IP, it'll show up as a public IP, but if you type in ipconfig on your local computer, your local IP will probably be like 192.168 dot something. Public and private IPs. Okay. So there's those ranges if my handwriting wasn't good enough. Again, just to reiterate, private IP addresses are not routable on the global internet. They are used for communication within a private network such as a home, office, or enterprise environment, and they're exclusive. Some other exclusive IP ranges. This is a Microsoft thing called a PIPA. So in the Windows operating system, we had a PIPA. It's called Automatic Private IP Addressing. This is a dedicated range for when your DHCP server A is misconfigured or reaches exhaustion. So we can see here in this little diagram, my DHCP server is a /27. So here's the usable range, including the network ID, the default gateway, and the broadcast address. This is the usable range. So even with a /27, even though that means a total of 32 host IPs, we only have 30 usable because the network ID, and then, the default gateway, of course, then the broadcast IP. So really you only have 29 usable, but the default gateway would technically sit like right here, right? And that'd be like a .1. Anyways, so you can see we have 30 workstations here though. So we reached exhaustion. So when we add PC31 here, it's going to reach out to the DHCP server and it's going to be like, oh, the DHCP, I got nothing for you. We're exhausted, This is our range. We got nothing for you, PC31. Windows operating system, if that's what's on this PC, is going to say, fine, I'll self-assign myself an IP address. And that's going to be in a PIPA in this range. Moving on. Another unique IP address is something called the loopback or the local host. This is a local IP address that's assigned to your NIC 127.001 that you could ping to make sure your NIC is working. It's also something that you can do when you're deploying like a web server in your local environment. You can access the local host. So let's say I deployed a web application. I'm just making it for production. So I'm in my test environment on a local machine. On my URL, on my web browser, I could type in the URL 127.001 or localhost, and that'll bring up the local website that I'm building on my local machine. So the loopback IP, it allows the device to send packets to itself, bypassing any network interface hardware. The local host is a host name that resolves to the loopback address and is commonly used in network testing and development. Okay, and then we get into subnetting. So as you see here, we start out with the /24, and then we can use variable length subnet mask to say, hey, well, this is my class C space, but I need to break that down even further. So if this is my enterprise, and I have 3 LANs that I have to account for, I'm going to subnet for this host requirement, I'm going to subnet for this host requirement, and build a subnet for this host requirement. So I'm going to have 3 networks, all built off this original /24. And as you can see, I need to break this down into subnets that meet the requirements. So a /25 gives us this range of 126 usable IP addresses. So that's going to work for the HQ. And we're going to start subnetting from the biggest host requirement. Next, Office A, the next biggest host requirement, 25 hosts, a /27 works. So building where this network left off at 127, we're going to start our network ID at 128, give it a /27, which equals 32 IP addresses, 30 usable, which is going to fit that host requirement. Here's our new network. Starting where this one left off at 160, we're building another network. 23 host requirement, /27 gives us 32 IPs, 30 usable. There we go, right? Now we can build another network. So that is the variable length subnet mask. Okay, now some more subnetting fundamentals, classless interdomain routing. You can see this is all our prefix lengths. So the CIDR is how we determine our network size and our host range and how many usable IP addresses we can have. Now our classes. So this is going to be our original classful IPv4 addresses, okay? So class A would be 1 to 126 in the first octet. Class B in the first octet would be a range of 128 to 191. Class C would be 192 to 223 in the first octet. And then class D is going to be 224 to 239 in the first octet. And this is going to be all for multicast, guys. This is the multicast IP address range. That's a one-to-many. That's what multicast does, one-to-many traffic, compared to unicast, which is one-to-one, or broadcast, which is one-to-all. A lot of streaming uses multicast. More on that later. And then we have class E, which is in the first octet, the range 240 to 255. These addresses are typically used for research and development within the network community. So we could have like a vendor that says, hey, when we do our local testing, we use a 240 address. That's the class E. Okay. Whew. Hopefully that video wasn't too long. Remember, I'm going to add a few subnetting videos into this playlist. Now, let's do our quiz. So question 1. Which IPv4 address is used for loopback testing on a local device? That's going to be 127.0.0.1. Awesome. Look at our explanation here. Let's go. Question 2. Which of the following is an example of a Class C IP address? Remember, Class C, like our legacy classful addressing, that's going to be 192 to 223 in the first octet. So we're going to go with D. Question 3. What does a piplet stand for and what is its function? So that's going to be automatic private IP addressing, and it assigns a private IP address when a DHCP server is unavailable or is exhausted or just not working, right? Question 4. Which of the following IP addresses is a private IP address? So that is going to be B. That is in the Class B private IP address range. Question 5. What is the primary purpose of subnetting in an IP network? So that's going to be A, to conserve IP addresses by dividing a larger network into smaller subnetworks. And let's go, we got 100%. So I want to thank everyone for viewing. Do not forget to like and subscribe. Smash that like and subscribe button, hit that bell, share with your friends, and thank you for viewing.